Yes.
Gravitational force is implied force and acceleration.
Yes.
Why is it continuing to speed up a terminal velocity? How drag exists?
Because it was given its speed. What's going to speed up the moon? No, it doesn't work that way. Gravity from the Earth is pulling the moon in. The velocity of the moon is perpendicular to that path. They're unrelated. You asked yesterday how the moon is getting further away, which you are right, it is. So the Earth's gravity can't be speeding it up. Any other comments, questions, concerns? Number 7. What is the acceleration due to gravity on the surface of the sun? So acceleration due to gravity and gravitational field strength, same formula. G equals GMM over R squared, 6.67 times 10 to the negative 11. The mass of the sun is 1.99 times 10 to the 30. The only difference here is we're not out where the Earth is. We're on the surface of the sun, and the radius of the sun is 6.96 times 10 to the 8. We square it. It's the same. The formula is the same. The values are different. And it's getting used to this idea that acceleration due to gravity and gravitational field strength are the same formula. They're both little g equals GMM over R. That should be squared. Not. And then you're just looking at whatever object's creating the gravity and how far away from the center of it you want to be. And I don't think it's 200 and... Oh, yeah, it is. Well, 274, 275. We rounded it to 275 before. Lachlan, good morning. What is a skill you think it would be awesome just to wake up one day really good at? Backflips. There we go. That is a practical, ridiculous skill. I love it. Okay. So, if there are no other questions about gravitational field strength or forces, the universal law of gravitational force, what I'd like you to do, and I asked you yesterday, if you have one to bring it, get out your computers. If you don't have a computer, we can go to the Science Lab and grab one. I would like you guys to spend a little bit of time playing with a simulation online. If you don't have one, you can sit next to someone who does. The two of you together, preferably not three. The two of you together can work through it on one. No, we are not doing 4 on 1. You don't have a charger, so you brought a computer that was dead? Okay. I've got a cord for you if you need it. If you need to reach your desk. I have an extension cord. Okay, so what you're doing, and I'll show you before I grab you a computer, is there is perhaps you've seen them before, a physics department out of the University of Boulder, Colorado called PhET. And what they do is they put together these simulations about a whole bunch of different physical phenomenon. And, I mean, it's obviously not going to be the same as you actually getting to push a fridge around, but where are we going to get a fridge that we can safely push around? Fridges are dangerous when you push them around. So what I want you to do is, once you've got your computer booted up, you're going to search forces and motion basics, as it says on your page, and then the letters PHET, PhET. If you open the first link that shows up, it's going to take you to this page. You hit the play button, and then it's going to open up your interactive simulation. You're going to go to the friction module. And then it walks you through what I'd like you to do. There's a bunch of different things that you can turn on and off. And it says which ones I want you to. It says to check the boxes for sum of forces, values, and masses. And then I want you to play with, there's a set of 6 questions there that I want you to play with. You can ratchet up the force. You can ratchet up the objects. There's boxes and fridges. You can put fridges on boxes and boxes on top of fridges. You can always reset it using this orange wheel on the side. Turn everything back on. And I want you to spend some time playing with this guy. You don't have a computer because you forgot to bring one. Yeah. The friction module is one of the elements. For the sake of time, yeah, by all means, I mean, you guys have 3 computers and a table for 5 of you, so partly saddle over to one of them so you can do it with you. That way, it takes some time for the school computers to boot up. So I will grab it for you. If you don't have one, I will grab a couple. There is one. That's probably more than that.
No, I'm not. He wants us at. He was like that. Yeah, they do, but they're not the right ones. It's forces in motion. What is it? Shit, my glass. I wear my glasses and see you last time. There you go. Yeah, it is. Are you touching my stuff? Leave me alone. I found it. Oh no. I cannot put this. Guess what? I found it. I searched it up. I need this extension cord. Negotiate. What's your computer at? Chill. You have to push box. You guys got it. Yeah, you guys got it. Oh, look at that guy. The box up there.
I was thinking about this.
What do you say we do? I'm at 200 though. Bro. They're pushing. Pack it. Put another person on. Whoa. Yo, can we only put them on top? That's very bad. And he's still. Oh, we can't move with the first one. Where'd he go? Yo. No. Bro, if you push the box and let it go. Yeah. Okay, I gotta look at the box and stuff. No. Shoot me dead, bro. Yeah, shoot me dead. Okay. You push his nerve. Remove it. Okay. Yeah, I can move that. I got no. There's no friction. Oh, he's sliding. There's no friction. Yeah, I know. Put 100 K to do that.
About a few, I don't know how dead they're going to be.
Other way. Oh, we got like fine. Let's go.
Okay. Forces and motion basics, and then you're going to the gravity one. Put your phone away. Oh. Whoops.
Should I borrow the extension cord?
Yeah, it's plugged into the wall right beside lock.
Look at that guy.
You guys. Let's talk about friction. Friction is created whenever 2 surfaces slide, and then in brackets I'll say, or try to slide, past one another. I mean, it's kind of intuitive. You experience this all the time. But we don't necessarily think about all of the implications here as deeply as we could. Like, my laptop is sitting here on my desk. We don't expect my desk and my laptop to start sliding past each other. And if it was using the same kind of analogy that we did with the person in the box, any sort of force applied to my computer would all of a sudden, a friction force would be generated opposing what I'm doing. That's what friction does. Friction opposes motion. Friction is created whenever two surfaces try to slide past one another, and it's important to note here, friction opposes motion. Right now, I'm not touching my computer, so you might suggest that there is no friction acting on the computer, but I don't know about you where you're sitting. I can feel a breeze over here where I'm sitting. That window's open, that door's open. I think the windows in DeVries' room are open. There's a little bit of a wind going through here. That wind is going to be felt on the back of my computer, so technically speaking, every time that breeze blows a little bit, there's going to be an effect of friction on my laptop. We don't think about it, because of course we say, no, the breeze isn't going to blow the laptop. But what if I like Vaselined the surface of my desk and took off those little plastic feet on the bottom of my computer? Or if I found a better lubricant, cooking spray, and it's all over my desk. Could the breeze move my laptop? Yeah. Theoretically, it could if friction's the only thing there, and we can find ways to minimize friction. Take off the plastic feet, cooking spray on the desk. All of a sudden, now that little breeze could start to slide my computer around on top, which would be weird. Things we don't think about intuitively. On the microscopic level, what's happening with friction is this. You've got one surface, and it doesn't really matter. Well, I'll draw it twice. You might think, as Kai said earlier, well, the surface is really smooth. So let's draw a really smooth surface. But what if I have another equally smooth surface? So there's your gym floor. You say, Kai, it's really smooth. What if we find another really smooth kind of surface, like a rubber shoe? A basketball shoe is going to be different than a track shoe because the way it's, or even like an indoor shoe versus an outdoor shoe, if you're playing basketball inside only, those shoes are going to have a different kind of tread on the bottom. If you have a really smooth surface on top of another really smooth surface, you're going to have a maximum amount of friction there. The entire surface is in contact with another surface, and they're not going to want to slide past each other very much at all. But realistically, most of our surfaces aren't that smooth, and so you get surfaces that look like this. You get, like, they have little bumps in them, kind of, as they just kind of are. Valleys and grooves. If you pull out a microscope and started looking at surfaces, you'd see that they're rough. And if I had another kind of equally rough surface, now maybe we're outside on the track, and I'm wearing a track shoe, not an indoor gym shoe, you're going to start to see that the tread on that shoe is also rough. And so what you get when friction is a thing is you get when two objects try to slide past each other, their grooves settle into each other. The grooves from one and the peaks from another, you can see it kind of in what I've drawn here. There are certain areas where they are interlocking more than other areas. Like right here for one, kind of here for another. Over here, definitely, they're a lot more grooved together. And it's these microscopic grooves, these peaks and valleys, that generate that friction. And the reason static friction is harder to overcome than kinetic friction is because when you stop pushing an object, it will settle, and the grooves will interlock that much more aggressively. And so you have to push a lot harder to overcome them. As soon as you've started to push to overcome, what happens is that these grooves and spikes on one surface and the grooves and spikes on the other surface start to slide past each other. And effectively, what are you doing? Something anyone in woodworking does all the time. When you slide a rough object over top of another rough object, what happens? You're sanding them. That's why it's easier to continue an object sliding. Because effectively what you're doing is you're allowing the object to smooth out the path that the rest of it is sliding into. But for a static object, the grooves are interlocked. So at the microscopic level, this is what you have, and I'll write out words here to explain it. The ridges and grooves on the two surfaces. Oh, I'm not even on the page. There we go. My apologies. On the two surfaces lock together. And that's what causes friction. If you can figure out ways to overcome that locking, you can reduce friction. Skaters do it all the time. If you have a really smooth surface like ice and a really smooth surface like a sheet of metal, there's going to be a lot of friction generated there. What happens when a skater steps onto the ice to reduce that friction? Do I have any skaters in the room? Something forms between the ice sheet and the steel blade. What forms? Sorry? Any kind of skating. Skating, like skating on ice. Yeah. It melts the ice ever so slightly. And that thin layer of water between the skater's blades and the ice surface is what causes these grooves to get filled in, and now you can have a skater moving at 30, 35 kilometers per hour over an ice sheet with, relatively speaking, minimal effort. Now, I know there's hockey players in the room. I know. Getting yourself up to those speeds is hard to do. But running at those speeds is impossible. So if you look at the relative efforts, it's a lot easier to do on skates. Sorry? Okay. This is where I'm going to stop today. I'll start giving you the equations. I'll start giving you some more definitions and examples tomorrow. Welcome to friction. We'll spend a couple days looking at it. And we're going to do a lab this week as well. Do not be away on Friday. This week, Friday. We're going to start a lab.